So today we're going to talk about UV spectroscopy in particular. So let's write that down here. Hold on, UV spectroscopy. And this is the last in the tools of the spectroscopy that we talked about in terms of structure determination. So again, just to review, we've already covered mass spectrometry and IR spectroscopy and proton NMR and carbon NMR. So the last tool that we're going to talk about today is going to be UV spectroscopy. And UV spectroscopy is interesting because it's, I guess the way to think about this would be it's giving us less information, and that's what your book says, less information, but very easy to interpret information. So let's do some background first of all. When we talk about UV, that stands for ultraviolet spectroscopy. And the region that we're talking about is the 200 to 400 nanometer region of the spectrum. So it's right next to the visible region, but at higher energy levels. Okay, so we can't see that region. The visible region is about 400 to 800 nanometers. So the UV region is next to, but at slightly higher energy levels. And to review, when we talk about spectroscopy in general, what's going on in spectroscopy is we irradiate the sample. Let's see if we can do that. Irradiate the sample with energy. And that energy has two choices. The energy can either pass through the sample, or it can be absorbed if the energy equals something that the molecule can use. So some kind of transition, something that the molecule can use, some kind of transition, for example, or something like that. Okay, and in particular, the energy in the ultraviolet region that we're talking about here is enough energy to promote an electron from a low energy state to a higher energy state. So, hold on one second, let's see if I can pull up. Alright, so if I have an electron in a low-lying state, so let's show an electron here at this guy. Let's say this is my electron. Then when I shine ultraviolet light at this molecule, it will promote an electron up to a higher state. So it'll move this electron up here. Alright, and we can refer to these low and high energy states as a HOMO and LUMO, respectively, and I'll tell you what those mean. So the HOMO stands for the highest occupied molecular orbital, and the LUMO stands for lowest unoccupied molecular orbital. So again, usually let's put in another electron here, okay? So we're starting with in the highest occupied molecular orbital, so the highest energy orbital that has electrons in it, we have two electrons. I shine UV light on my molecule. What that does is it promotes one of these electrons from the HOMO up to the LUMO, the lowest unoccupied molecular orbital. And this is particularly the case for conjugated bonds or conjugated systems. So we've already talked about conjugated systems in the context of conjugated dienes and Diels-Alder reactions. Now the amount of energy required to go from the HOMO to the LUMO for UV spectroscopy refers specifically to promoting electrons in pi systems. So we can think about this HOMO, or these two electrons in the HOMO, as being in a pi bond, in a double bond system, and we call this then a pi molecular orbital. This orbital here, the LUMO, is an anti-bonding, what's called a pi star molecular orbital. And again, with UV spectroscopy, we're promoting an electron in a double bond alkene from the pi to the pi star orbitals, resulting in an absorption in the ultraviolet region. Just to be clear, if I do not have a double bond of some sort in my molecule, there will be no absorption in the UV spectrum at all. Practically, how do I do this experiment? I am going to scan all the wavelengths, so shine light at the molecule, shine energy at the molecule of all the wavelengths from 200 to 400 nanometers, and then monitor where I reach a match. So where does the energy of the light shining in match the energy necessary to excite an electron from the HOMO to the LUMO. And wherever it matches, that's where I will see an absorption. I can define absorption, and your book goes through this, equals the log of I0 divided by I. Okay, and I can define I0 equals the intensity of the incident light, that's the light that I shine in, and I equals the intensity of the light that is transmitted. And the log of that ratio is the definition of the absorption of the molecule. I can also relate the absorption to some other parameters of my molecule. Hold on, I don't even know if I could do Greek letters here. Let's try to do Greek letters in a Word file. Alright, so I can define or use this equation that I'm showing you over here to explain what absorption is, okay? And here I'm defining epsilon. So epsilon is defined as the molar absorptivity of the species. A is my absorption, and C is the concentration of the species. L is the path length is the definition. That means how wide is the cuvette that I am shining things through, measured in centimeters. And it turns out that the molar absorptivity, this epsilon, is a constant for any given species. So each molecule has a characteristic molar absorptivity. Therefore, I can use this equation to figure out the concentration of my molecule. So if I know the molecule, I can figure out the concentration by rearranging the equation. C is now the absorption divided by epsilon times the path length times the path length. So again, because each molecule has a characteristic molar absorptivity, I can use this equation. I can measure the absorption of the molecule. I know the molar absorptivity. I know the path length, or the cuvette size that I'm using. I can use this to figure out the concentration of the species whose absorption I'm measuring. And now, more generally, talking about UV spectroscopy, again, we've said only molecules with double bonds have absorption in the ultraviolet region. More generally, the energy of that absorption relates to the extent of the conjugation. I'm going to write that. Absorption relates to extent of conjugation. This means that, what does this mean? That the more conjugated the molecule, the lower the gap between the HOMO and LUMO, and the longer wavelength, lower energy light, The smaller is better. The smaller the gap between the HOMO and LUMO, and the longer wavelength or lower energy light is required to excite the molecule, the electron, from the HOMO to the LUMO, which means that very conjugated molecules actually have absorption in the visible region. So when I see colored molecules, that means that they are absorbing light in the visible region. That's because they are exceptionally conjugated. An isolated double bond has less, higher energy, requires a higher energy light to excite the electron from the HOMO to the LUMO, and that's going to be absorbing in the UV or the ultraviolet region. Your book has a table of where certain conjugated molecules absorb light. So let's see. So this is a picture that I'm showing from your book, which has the ultraviolet absorptions of some conjugated molecules. So if I have, for example, let's see, these double bonds here, 2-methyl-1,3-butadiene, that is absorbing at 220 nanometers. If I now look at this case here, where I have 1, 2, 3, 4 conjugated double bonds all together, that absorption is now at 290 nanometers. Okay, so that's a longer wavelength and therefore a lower energy. That's because the more conjugated the system is. So here, the more conjugated, the smaller that HOMO-LUMO gap. All right, and I can see that when I have 4 double bonds conjugated, it's 290. When I have just 2 double bonds, it's 220 nanometers. When I have 3 double bonds, as you would expect, that's at 258 nanometers. Okay, so that's intermediate in terms of the energy levels between having just 2 double bonds and having 4 double bonds all conjugated together. And the more, again, the more conjugated I make these, the longer and longer wavelength the absorption is going to be until I start moving into the visible region of the spectrum. So hold on one second, I'm going to pull up some conjugated systems that absorb light in the visible region of the spectrum. And here in particular what I'm showing is the UV absorptions of fused aromatic ring systems. So benzene absorbs at, here's benzene, its absorption maximum, lambda max, that's what we call this system here, is lambda max, the Greek letter lambda, is 203 nanometers. If I now put 2 benzene rings together, this is now naphthalene around 220 nanometers. Anthracene absorbs around 260 nanometers. And this compound here, this fused tetracene, so 4 benzene rings all fused in a row, is now at around 300 nanometers. And I can keep pushing that further and further into the visible region, so longer and longer wavelengths corresponding to smaller gaps between the HOMO and the LUMO. Again, that's what's dictating the UV visible absorption, is how big is the gap between the HOMO and the LUMO. So I'm just going to pull up one more example. Hold on here. So some pigments that we see a lot, like beta carotene, for example, this is what its UV spectrum looks like. It's absorbing in longer than 400 nanometers because it is so highly conjugated that its absorption, the energy gap between the HOMO and the LUMO, is small enough that we're seeing it at around 400 nanometers. So that's pretty much all I have to say about UV visible spectroscopy. You can look in your book again for some tables, and I'm going to upload also some problems in terms of how we can get useful information from the UV visible spectrum.